Hi everyone, I'm Dev and today I'm going to present my capstone project, which is Brain2Action. That means converting your thoughts into actions. And first of all, let me give you a brief background about what is the brain-computer interface. So BCI means connecting the software applications with your brain signals. So there are so many ways to connect that. So the most of the cases uses is using machine learning approaches to map the signals to classes. And the key applications for BCI is it's helpful for decoding the neural patterns from EEG signals to understand the intents of the human, and it enables robotic control via your brains, and therefore it helps people with disabilities to um, make certain movements with robotic implants. And let me now introduce the system components. So for this project, I have used EEGNet architecture, and we have I have developed a training strategy based on the results I got from the trial runs, and we I have created a web application to present my project, and it's an end-to-end pipeline, so anyone can use it with the correct data format and data files. And the objectives for this project is to classify whether the subject is thinking about moving left or right arm, and also there are another sub objectives like comparing the training strategies to identify and pick the best one, and to demonstrate how it can be leveraged into real-time applications. So what is actually a BCI and how we detect the signals? So the term BCI means brain control interface, but the brain part, that means capturing the signals from your brain's different regions. So here in the example, we can see on the screen that there are so many regions and electrodes are there. The black dots and the blue dots are the electrodes, the red dots are the ground. So there are so many points from which we can get the data, and I have used points C3, CZ, and C4 for getting the data. I've used just three channels. And what is actually motor imagery? It is means the mental simulation of a movement without actually doing the movement by by moving your arm or leg or any other limb. So left hand motor imagery means the subject is thinking about moving their left arm, and right hand motor imagery means subject is thinking about moving his right arm, and the goal is to distinguish which hand movement did subject thought whenever the model is continuously model starts predicting. So let's check about the placements of the electrodes we use. So here in the image we can see that the C3, CZ, and C4 are the locations where we have selected where we have put the electrodes to detect the brain activities. So the work of the C3 electrode is to get the signals whenever subject is thinking about moving their right hand, and the C4 is helpful to detect whether the subject is thinking about moving his left hand. And the device we have has a sampling rate of 250 hertz. That means 250 samples per second, and we have frequency filter to filter the signals we got within 4 to 40 hertz. That has the mu band, which is 8 to 12 hertz, and beta band, which is 13 to 30 hertz. And we have the trial duration for the experiment is 4.5 seconds, where we have total we have 7 seconds of trial, but we trim the trial to get the motor imaginary part only. So here is the sample data which I have selected for subject B1. So here in the images we can see that whenever the subject is thinking about either movement, the certain part of the brain activates and it produces event related desynchronization. That means if subject is thinking about moving left, the activities will be on the right will be less due to event related desynchronization, and here that we can see in exactly like 1 second where subject actually starts thinking about the movement. And on the in the second graph I have plotted the ERP diagram for subject B1 as well, that we can visualize the subject related desynchronization at 1 second. So let's look at the systematic investigation from the signal analysis. So what are the research questions for this project? So first one is, how effectively can deep learning architectures classify the motor imaginary movements based on the EEG channel, like based on the minimal 3 EEG channels? And how robust are the trained models to be able to identify the actual movements? And which training strategy, subject dependent or subject independent, should be used for training? And how can the trained models be integrated into the real world applications? So I have divided this whole project into 4 phases. First one is exploratory data analysis. The second one is model development. The third one is model training and evaluation, and the fourth one is the actual application interface to visualize the models performance. So the data set I have used is BCI Competition 4 and it has 9 subjects, and the format of the files are GDF files, and we have total 300 to 400 trials per subject. That means 27 to 3600 trials in total, and we have 3 training sessions and 2 evaluation sessions, and we and the class is almost balanced, as there are no huge class imbalance in the data. And we have 250 samples for each second, as I already explained. Due to the device capability, we only get 250 samples per second. And here is my pre-processing pipeline, where I first bandpass filter the signals from 4 to 40 hertz. Then I select then I notch filter the signals to 50 hertz to remove the noise. Then I select only 3 channels and discard the EOG channels, which are the eye movements and the other facial movements. And then we have epoch extraction, that means trimming the trials to get just MI period of 4.5 seconds. And then I'm processing the data through Z-score normalization to remove the baseline from the data. And then we have the trial validation, where the trial mark bad trials should be removed. So that includes moving the limb movements as a part of the trial, so we cannot use the trial for training. And here is the model architecture that I have. So as you can see from the diagram, the I have selected EEGNet for that, because it's a benchmark model and it's lightweight and easy to train and already been published in many publications. So what the structure is, it first processes the signal in time domain, then it processes the signal across the channels, and after the both the processes, it combines and processes the created outputs, and at the end it classifies the signals into 3 class. One is for left, second one is for right, and the third one is for still. So for the training strategies, we have RM optimizer, we have cross entropy loss function, we have all the stopping configured as well. The batch size has been selected 64 because it performed well. It is not heavy. It is not passing too much data to the model at once, so that a batch size 64 is good. We have maximum epochs of 500. And there are 2 main strategies I have decided to use. Is subject dependent. That means the model for each subject will be unique, will be trained on the subject's data itself, and the model should not contain data from other subject, should not be trained on the data from other subject. And the second one is subject independent, where we start training model as soon as we start getting data without noticing about the subject. So if we have 2 subjects and we train model on that, we can test it on third one. So that means a subject independent training. So I have decided to try both and pick the one with efficient accuracies. As you can see from the results, the subject independent performance highly outscored the subject dependent performance highly outscored the subject independence performance. We got 63.17% accuracy with 9.59 plus or minus error ratio. And for subject independence, we got only 50, which is just chance level accuracy. And the paired test also proved that the subject dependent is also it's a very robust and good method that can be used. And here is the heat map of the accuracies for each subject. So we can see most of the green region are from the subject dependent, not the subject independent. Hence, I have decided to use subject dependence training method. After that, here are the explanations of why I have selected the subject dependent trainings, which I already explained in my previous slides. And here's the complete system achieves this. Here is the total system validation from the experiments. So we have determined that the model is able to identify the left and right movements from 63% accurately, and the model is trained on 9 subjects and can perform good for all of the subjects. And we have the mean accuracy of 63.17, which is state of art accuracy for this system. And we have implemented a good training pipeline and data preprocessing and training pipeline that can be used for the similar data if we have another subjects. And also for this, I have created a web application that helps user to visualize the model's performance by seeing the movements of the smiley face on the screen. Whether user is thinking left, the smiley face will move to left. If user is thinking about moving right, the smiley face will move to right. That at the last of at the end of the run, it will also show the accuracies as well. So the applications for frontend created on React, the backend created on Django REST, and it is using the model is via TensorFlow, PyTorch, and the I have used PyTorch because it's very flexible, and the GPU used from PyTorch is very good. It's easier and easy to implement. So the key findings from the projects are we got 63.17% accuracy versus 50.42% for subject independent. That means subject dependent accuracy is good, which was our research question. The EEGNet architecture is also good as it's able to identify the movements from the signal, and we have created a complete pipeline, and we have tested that pipeline on real world application as well. So the project's contribution will include complete end-to-end pipeline to train the data to classify motor imaginary signals from brain, and it can be flagged as benchmark model. Here are the future work recommendations to enhance the efficiency of the model and the pipeline. So we definitely need more data, as we are just using 9 subjects. If we get more subjects, we can validate and monitor the drifts of the models. And we need a higher like high compatible devices to get data that can capture multiple regions of brain at once at very high sampling rate, like 1000 hertz or more than even 2000 hertz. And we need better quality of electrodes to get the exact signals from the brain. There should not be any noise or something that can lead model to train falsely on the noise. And we can also modify the model architecture to efficiently to increase the current accuracies to a better extent by adding a few more convolutions, and by changing the training parameters as well. And for real world application, I would say we need to find something that can reduce the latency for model inference and model prediction time. And other than that, we need to integrate the model with the robotics systems like ROS and simulators like Isaac Sim. So the long-term vision for this project is to make brain computer interface affordable. As we can see, the pipeline is very simple. It can be implemented in like very low cost softwares, and that anyone can use and take benefit of that, and can able to control and make certain movements that they cannot do physically. So the long term goal is to help people to achieve better quality of life. Thank you so much. That was my project, and I hope you understood the idea of my project and the results of my project. And if you do have questions, I have my contact details over here, and you can always try to reach out to me via GitHub or via email as well. Thank you so much. Hope you have a good day. Bye bye.